This week it's a seminar. Today we are really happy to have François Foucart talking about binary neutron star mergers and the quest for gold in the universe. So François Foucart did his PhD at Cornell University, then went on for a postdoc at the Canadian Institute for Theoretical Physics. Then he went on with an Albert Einstein postdoctoral fellowship at Berkeley, and now is professor at the University of New Hampshire. So the stage is yours, and thanks.
Thank you, and thank you for having me here today. In this presentation, I would like to give you an idea of how we can use the collision of extremely compact objects like black holes and neutron stars, hundreds of millions of light years away, as a laboratory to study physics in extreme conditions, specifically very high gravitational fields, very high space-time curvature, and very high densities. And before I get any further, I want to mention that I'm very happy if people have questions during the talk and interrupt the talk as we go. I don't mind if I don't get to the end of my slides, I probably won't. I would rather have a discussion if there is any reason to do that. We're going to focus on these collisions of compact objects, black holes and neutron stars. And before I get into that, there we go. I would like to take a step back for anyone who does not work on black holes and neutron stars to give you an idea of the kind of scale that we are considering here, the kind of object that we are considering here with these systems. So black holes are fairly well known as objects with enough mass in small enough regions such that nothing can escape in Newton's version of gravity, the gravitational force coming from the black hole, and in Einstein's theory of general relativity, the region of strong space-time curvature around the black hole from which nothing can get out. And the boundary of that region is called the event horizon of the black hole. And then to give you an idea of the scales that we are considering, if you were taking the sun and making it a black hole, you would need to make it a radius of somewhere between 1.5 to maybe up to 10 kilometers, depending on how the black hole is rotating. So the mass of the sun within a very small city. And if you were to do the same for the Earth, you could put the entire Earth in about this size. That's about the size of a black hole, the mass of the Earth. So we are going to be talking about extremely compact objects with very strong gravitational field right outside of that event horizon region. And in this talk, I'm mostly going to focus on black holes of a few times the mass of the sun, so in the 10-kilometer range or so. But we have actually, practically, because these objects are so small, we have actually only really managed to spatially resolve 2 black holes, and they are in a very different range, including this one from the very famous picture from the Event Horizon Telescope, which is a 4 billion solar mass black hole in a neighboring galaxy called M87. So this is one object for which we actually can resolve the shadow of the event horizon of the black hole. There's a second one, which is the one at the center of our galaxy, which is about 1,000 times smaller, only 4 million solar mass, and significantly closer. Because of those very small size, those are the only one for which we can actually have spatial resolution to see the object. Everything I'm going to talk about is kind of integrated quantity over the entire system that we are considering. We don't get spatial resolution. Neutron stars, in terms of compactness, are kind of the next best thing, and in terms of actually using them for nuclear physics, even more interesting than black holes. They are objects that go from a little bit more than 1 time the mass of the sun up to an unknown maximum mass that's somewhere between 2 to 2.5 solar mass or so. Right? So in that range, we have neutron stars with radius that are somewhere between 10, 14 kilometers or so. As we'll see, the actual radius of neutron star is one of the important open questions that we are trying to answer by studying their collisions. And if you do the math and try to calculate what kind of density this corresponds to, you will find that it is of the order of 10 to the 15 grams per centimeter cube. So extremely high densities that are comparable to what you find in atomic nucleus, but for an object of roughly the size of a city. Right? So this is going to make them extremely interesting objects to study nuclear physics, because this very high density and relatively cold environment is a regime of physics in which we cannot actually reach on Earth in laboratories. We can get very high densities and very high temperature by colliding particles at high energy. We know to do that very well. but we can't very easily get the very high densities and cold temperature that are the center of neutron stars. And that's what makes neutron stars a very interesting laboratory for nuclear physics. Okay. What? I'm going to use the arrows. No. All right. Or maybe it's going to change 5 times. No, we'll see. All right. So to summarize the kind of things that we can actually study when we have two of these objects colliding with each other. Right? The first thing that I'm not going to talk too much about here is that we can use them as a probe for understanding of gravity, whether we are talking about Einstein's theory of general relativity or whatever might lie beyond if we try to get into quantum gravity or any beyond Einstein theory. This is because, again, these are the objects with probably the strongest space-time curvature in their neighborhood that we can actually observe in the universe. And especially when they are colliding with each other, because Einstein's theory is nonlinear, we can actually probe the nonlinear aspects of the theory as the two objects are merging. And this is really only possible if you have these compact objects colliding with each other. We can study neutron-rich dense matter, which I'm going to come back in a minute. And we will see that these systems eject material in which nucleosynthesis, the production of heavy elements, is expected to happen, including the production of elements such as gold, uranium, platinum, which we observe in the solar system and on Earth, but whose actual astrophysical origin remains very uncertain. And one of the things that we'd like to do with the study of these systems is determine whether these heavy elements are produced in neutron star mergers or whether we need some other source of heavy elements. So whether most of these elements are produced in neutron star mergers or whether we need another source. We know that some of them at least are produced in mergers. Then there are other questions that I'm not going to really get into in this talk, but that can be interesting and addressed with these systems. What are the formation mechanisms for black holes and neutron stars? Something that we can probe by actually looking at the type of black holes and neutron stars that we observe when they at the time at which they collide. Neutron star mergers and black hole mergers can be used to study cosmology for the moment, mainly through the measurements of the Hubble constant. And then they are the source of some of the highest energy events that we observe in astrophysics, gamma ray bursts. And we can use the study of this system to try to understand how these events are even produced. These are the kind of questions that we can consider when we have these extremely dense, very strong gravity objects colliding with each other. All right. So I would like to give you a bit of an idea of how we go from studying the properties of neutron stars to actually understanding nuclear physics in very dense matter. The general idea is that if you have a neutron star, as you go from the surface to the inside, you get to higher and higher densities. And at the densities that we are talking about, electrons become degenerate very rapidly. They already get degenerated in a white dwarf. And if you have fermions like electrons densely packed together, they cannot share the same energy state, and so they have to get into higher and higher energy states. That means that at some point, if you get to high enough densities, the energy of an electron, degenerate electron, plus the energy of a proton becomes larger than the energy of a neutron. It's kind of the inverse of what we are used to in normal life. And then it is favorable for the electrons and the proton to annihilate into a neutron. That's also how we get to a state of matter, which is mostly neutrons inside the dense neutron star, which is why we call them neutron stars. So inside the neutron star, we have about 90–95% neutrons, and the rest is protons. And then when we go even deeper into the core of neutron star, we reach a regime in which we don't even know what physics looks like. At some point, most likely there is a phase transition to, among other things, a quark-gluon plasma, but there could be also production of other particles involving strange quarks, for example, which could also affect the properties of your matter inside neutron stars. We just don't know what we cannot predict it from ab initio calculation at this point. Now, if you have a theory, nuclear physics-based theory for what happens in that dense matter, you can use statistical mechanics to derive things like the pressure inside the neutron star. Once you have that equation of state of the neutron star, you can use that and Einstein's theory of general relativity to calculate what the structure of a given neutron star is. And from there, gets things like this, which is the mass versus radius relation for any given theory. So if you, any of these curves here is a nuclear physics theory, and any of them gives you a different prediction for the mass versus radius of neutron stars. And then if you have an astrophysical macroscopic observation of a neutron star that gives you some constraints on the mass or radius of neutron stars, you can actually determine which of those equations of state are consistent with the observations and which of them are ruled out. And that's how you can actually start backtracking towards the nuclear physics. And for example, on this plot here, you can see a few of these important observations that have been done so far. At the top, you see some those horizontal lines. Those are simply called mass measurements, just mass measurements, but for very high mass neutron stars, of 2 solar mass and above. The fact that these neutron stars exist means that these curves need to get at least here to 2 solar mass. Anything that does not get there has been ruled out by now. That is why the measurement of these high mass neutron stars is important for nuclear physics, and why, if, we were not to measure a neutron star around here, this would be a very, very important discovery. It will rule out a lot of those equations of state. And then there are 2 other sources here. The purple dots here are measurements done by the NICE collaborations of mass and radius using the rotation of hotspots on the surface of neutron stars. And then the green dots are the gravitational wave measurements from the collision of 2 neutron stars that I'm going to describe in a minute. And so those gives you a combination of mass and radius of the neutron stars, which allow you to possibly rule out some equation of state. So something here is not consistent with gravitational waves. Something that would come only up to here is not consistent with the existence of 2 solar mass. So those things which, 10 years ago were still considered possible equations of state for neutron stars have now been ruled out by observations. Any questions so far? All right. And then to give you an idea of the kind of elements we are talking about when I'm talking about nuclear synthesis from these events, the kind of things that may or may not be produced in neutron stars are all of the light yellow elements on this table, table. Basically, anything that is light yellow is produced in very neutron-rich environments through the rapid neutron capture nuclear synthesis process, which I describe in more detail later. So we know that. What we don't know is where most of that R process happens. Neutron star mergers are one possibility because it requires a neutron-rich environment. And if you eject matter ripped apart from a neutron star, you are pretty sure that it is neutron-rich. So that's one place where we know it can happen. The question is, does it happen often enough in the universe to explain what we observe? Does it produce the right pattern of elements? Those are the questions that we have to answer. And if not, then we actually have to ask ourselves what else can produce these elements. And one very common counter-proposal to the neutron star merger scenario is some type of core collapse supernova. There are different proposals in that respect as well. So it's something that we don't know, but with a better understanding of how often do merger happens and how much matter do they eject, we can actually try to start to address. Okay, so now I'm going to first show a few movies that give an idea of what these events look like in simulations. Again, there is no spatially resolved observation of any of these systems, so this is all simulations that I'm going to show you. Right. The first movie is showing some measure of the space-time curvature around 2 orbiting compact objects. So according to Einstein's theory of general relativity, any of those compact objects create a strong space-time curvature around it. And as they move, they drag that curvature along and create ripples of space-time curvature through the surrounding space-time. So the gravitational waves, which carry around energy and angular momentum. That means that the binary, which is initially far apart, is going to slowly decay to be closer and closer together, orbiting faster and faster. That means that the frequency of the gravitational wave increases, the amplitude of the gravitational wave increases, and the rate at which it's losing energy, so the rate at which it's coming together, is also increasing. So it's going to move faster and faster and emitting more and more gravitational waves at higher and higher frequency. This is what is called the chirp of the gravitational wave signal, that increasing in frequency and amplitude pattern that we expect for any compact object binary. So here we are getting, this is a binary black hole simulation, by the way, and we're getting to the point where the 2 black holes are going to collide and merge in one last burst of gravitational wave. And then in this case, you are left with just a single black hole, which by that point, yes. So if you were talking about solar mass black holes, roughly, this entire thing would probably be maybe 1/10 of a second. Roughly speaking, this is all very fast. Yeah, I'll come back to that, but many of the simulations that I'm going to show, they are basically tens of milliseconds at most. This is all very short time scales. Yeah. Now, because this is binary black hole, you can actually scale it with the mass of the black hole however you want. So if these were linear sources, you know, it could be 1,000,000 times longer. And if they were supermassive black holes of billion solar mass, 1,000,000,000 times higher, right? But for the LIGO sources, a fraction of a second. Right. And then from a detection point of view, you know, if you have a gravitational wave that was passing through the Earth, let's say coming out of the board here, the effect on hanging test masses would be that in one direction, they appear to get farther away from each other. In the other direction, they appear to get closer, and that oscillates back and forth. And so the way this is detected is through these very long interferometers, LIGO, Virgo, CAGRA. In the case, this is the LIGO detector, which is 4 kilometers long. And if one of the arms becomes slightly shorter than the other, or slightly longer than the other, then you get an interference pattern at the exit of the interferometer that changes. Basically, these interferometers are tuned so that if there is no gravitational waves, there is destructive interference between the two arms. And then if one of the arms gets slightly longer or slightly shorter, you start getting a signal at the exit of the interferometer. Right? And the light itself goes, you know, many ways through these arms. This is an extremely precise measurement. You need to make a measurement of the order of 10 to the minus 21 times the distance of the interferometer, so about 10 to the minus 18 meters is the measurement you have to make. But this has been done, you know, many times by LIGO-Virgo collaboration. One thing to note, because of the small amplitude of the signal, is that for most signals that have been detected so far, in order to just detect the signal and even more to interpret it, you first need a good model of what the signal looks like, because the way they are detected is by comparing this data stream to known models. Right? So one of the role of both analytical modelers and people like me doing simulations is to actually try to help these detection process by building and calibrating waveform models that can then be used to analyze and even detect these signals. Now, if there is a bright enough signal, then maybe you don't need that, but that's pretty rare. Now, I'm mostly focused on neutron star mergers. Those are the ones that allow you to do nuclear physics and to do nuclear synthesis. Let me show you what happens now if I have a neutron star colliding with a black hole. Now I'm going to focus more like on the last maybe 10, 20 milliseconds of the system in this case. So you have the neutron star here, you have the black hole here. The grid here is just the simulation grid. It's not physical. And as in the black hole system, the neutron star gets closer to the black hole due to gravitational wave emission. And eventually, the tidal force from the black hole rip apart the neutron star. And then you eject some material in the tidal tail, which is going to expand into the surrounding galaxy. And you form an accretion disk around the black hole. So maybe like 1% of the matter or so is ejected, up to maybe 10% is in the disk, and everything else falls into the black hole. These numbers are approximate and change a lot depending on the parameter of the system, which is in some cases there is even nothing left outside. But in this case, the neutron star was ripped apart. And so now that we have matter ejected into the surrounding medium, we have an accretion disk black hole system. This means that we are going to not only get gravitational waves, but we're also going to get powerful electromagnetic signals coming from that material left outside the black hole. That's where the EM counterpart comes from. Nope. Okay. Okay. So if you have two neutron stars instead, the beginning is pretty much the same. The objects get closer together to the point where they get into contact. Now I'm going to show you, this is the horizontal slice through the merger. On the right, you have the density. On the left is the magnetic energy. This is at the point where the two cores are first getting into contact with each other. And there's a strong shear between the two neutron stars. They are moving at 30% of the speed of light and colliding tangentially. Right, so this is a very rapid process. Again, it's going to be a few milliseconds. And the strong shear is going to create Kelvin-Helmholtz instability in between the two neutron stars. And at the same time, the two cores are going to collide, rebound, and oscillate for a while. And so we have ejection of matter from the tidal disruption as before, but also from the collision of these two cores, which very hot material that is being ejected as the two neutron stars hit each other at very high speeds. And then eventually the system is going to settle to a single neutron star surrounded by an accretion disk with a very strongly magnetized interior, which can get easily to 10 to the 16 Gauss inside the neutron stars. Right? It can grow from normal neutron star magnetic field to 10 to the 16 Gauss within the roughly 1 or 2 milliseconds it gets for the cores to collide and merge into a single neutron star. That's one possible outcome. There, it could also collapse immediately to a black hole if the mass is high enough, and that's going to be important for what kind of electromagnetic counterparts we can get. So there's a wide range of possible outcomes, but this is the one that happens typically if you have relatively low mass systems that don't collapse to a black hole. By the way, one thing that's going to be important for later, you might see that the magnetic energy here is decreasing over time. This is not correct physics. This is a problem in the simulations. It's worth emphasizing is that one aspect of these simulations that if you want to properly resolve the magnetic effects, which are going to be crucial for ejecting matter, you need very, very high resolution in a way that is generally not affordable for most simulations. And in order to do that, either you get to those very high resolutions somehow and spend hundreds of millions of CPU hours on a single simulation, or you need some sort of subgrid model like the one we were talking about and that you are developing, in order to actually get those large-scale magnetic field without getting to the detailed simulations of the meter-scale physics that is needed otherwise. So this is actually a failure of the simulation in some ways. In the way that we know we are failing is that the magnetic field decays because we don't have enough resolution and dissipates due to the finite grid resolution. So to put it kind of together on the what we see from neutron star mergers and what happens, right? First, you have that long inspiral. The actual time scale for the inspiral is not seconds or milliseconds, it's billions of years. But we see the gravitational waves only for the last maybe seconds or so. It depends a lot on the mass of the system. It can be a bit longer than that for low mass neutron stars. And then that's the part that we see with like a Virgo Cagra. And then you get disruption of one of the neutron stars, both neutron stars, an ejection of matter into the arms, you get collision, an ejection of shock material from the collision. That lasts a few milliseconds. And then you have either a black hole or a neutron star at the center of your system, depending on the mass of the system, surrounded by an accretion disk. That accretion disk is going to evolve potentially up to multiple seconds. But over the first maybe 100 milliseconds or so, is going to start producing winds that are driven by magnetic fields largely, as well as if you form a large-scale magnetic field, relativistic jets that are going to power the gamma ray bursts. Right? And this is where what I was talking about, getting the large-scale magnetic field correct is really important. If you don't get the growth of magnetic field correctly, if your magnetic field decays in your simulation, you will never get that jet and you won't properly capture the magnetically driven outflows. Right? So this is where there's a lot of very complicated physics coming on. We will see that neutrino transport also play an important role at that point, which something that nearly never happens otherwise in physics. That neutrinos generally just pass through things. Okay, so now you have two important sources of matter being ejected into the galaxy. You have the merger itself, and then you have those disk winds. All of those are relatively neutron rich, and they are going to go through rapid neutron capture nucleosynthesis, which we will see in more detail in a few slides, but basically is a process by which you first form very neutron-rich elements that then radioactively decay towards the heavy elements like gold and uranium that we are interested in. Right? The actual neutron capture process happens over maybe a second or so, but then you have a very long time over which things radioactively decay towards more and more stable elements. And that releases energy, of course. Now, initially, the photons that might be emitted from that very hot material, that is heated by the radioactive decay of the R process, are just trapped into the matter. The matter is such high density that the photons cannot escape. This is also the case during everything here. The photons never escape anything in these situations. The photons are trapped up to the point at which the material expands and becomes low enough density that it becomes optically thin to photons. And when that happens, then the ejector radiates as an optical infrared signal. But that takes from days to weeks after the merger. You start seeing a signal maybe half a day after the merger in relatively blue wavelengths, and then you start moving towards redder and then infrared wavelengths over time scales of days to weeks. That is what is called the kilonova, the signal that is powered by the decay of the R process ashes. And it requires to follow what's happening to your system for much longer time scales than the milliseconds that we are talking about for the merger. And potentially there is also a radio transient that we haven't seen so far, which is due to the material slowing down as it hits the interstellar medium. But that might be a signal that could happen over decades after the merger and is relatively weak. So it's a very hard detection to make, and we haven't made it so far. Now, we've seen radio emission from the jet afterglow.
How close does it need to be?
Actually, the more interesting part to know whether we can see it or not is whether the surrounding interstellar medium is at high or low density. One of the reasons it might be very hard to see it is that we expect many-neutron star merger to be slightly offset from the denser regions of galaxies. And then the surrounding interstellar medium is very low density, and it takes a long time for the material to slow down. But if, on the other hand, you were closer to the center of a galaxy where the ISM is higher density, you might see it evolve on a few months to a year time scale, and it's the same energy being radiated total, so you would see much better. I exactly how close it has to be for any given density, I don't know it off the top of my head, but there are many good papers by Kentaro Tokizaka and Ehud Nakar that looks at that kind of things, among others. So I can take your reference later if you want, but I don't know off the top of my head. Any other questions on this? By the way? Okay. So that's kind of the overall the kind of process that we are interested in studying, and we want to try to use the merger itself and the gravitational waves and the kilonova process to understand both what happens inside of neutron stars and then how do they contribute to the formation of heavy elements. Okay. So let's start first with gravitational waves. We can also say, okay, how do we use gravitational waves to actually study the interior of neutron stars? And the general idea is shown on this plot. This is the gravitational wave signal as a function of time, close to merger. The time scale is some arbitrary coordinate, but for roughly solar mass objects, this would be about 20 milliseconds of evolution total. Again, it scales with the mass of the object, so it's kind of arbitrary, but tens of milliseconds. The blue curve here is for two black holes of equal mass, no spin. The red curve is a black hole and a neutron star, same parameters. The white curve is two neutron stars, also the same parameters. And initially, there is no difference between these waveforms, but when they get close together, the neutron star gets distorted, and that impacts the waveform. And you can see that systems with neutron stars, the white and red curve, start evolving faster than systems with black holes. By evolving faster, I mean the amplitude grows faster, the frequency increases faster, and they get to merger earlier. And you can see that leads to a very small dephasing of the signal that we can try to measure. Physically, what happens is, as the neutron star is disrupted, you take energy, sorry, not disrupted, distorted by the field of by the tidal field of the black hole. You take energy from the orbit into the distortion, so you lose energy that way. And on top of that, your distorted neutron star orbiting with a black hole or neutron star companion is itself a time-varying particle, and so it emits more gravitational waves than just the binary system. Both of those effects lead to faster evolution of the system towards merger.
What is the mass of the black hole?
Well, this will not be two real black holes because they're too low mass. So I think these simulations were meant to be like 1.4 plus 1.4 solar mass, just to see the effect of. But in the black hole simulations, it's entirely rescalable. So it was probably meant for higher mass systems. I just rescaled it to 1 solar mass, 1.4 solar mass objects.
So when you said that there is neutron star no spin, it's assuming that the neutron star are not rotating.
Yes, that's right.
I just think that
The spin of the neutron star is 0. Yes. Yeah. Now, of course, real neutron stars do spin, but again, the orbital time scale at the time of merger is millisecond, and so if you have a 1 second period pulsar, it doesn't matter. It's basically non-spinning. if you had a millisecond pulsar that was still a millisecond pulsar at the time of merger, so very late in its evolution somehow, right? Then the spin matters. So this is the case for the green curve, for example. Here, this is a very rapidly spinning neutron star, like again, 2 or 3 millisecond period, something like that. And then you get a significant effect from the spin of the neutron star. But you need to somehow have that kind of millisecond pulsar at the time of merger, which is, requires some probably dynamical capture in a cluster or something like that of a young neutron star. So it's not a particularly favored method yet.
And after merger, that's
yes, good question. So indeed, if you look at this plot, it's pretty clear that this is a very small effect. There is a lot of stuff happening here. At the black hole, they get close together, they form a single black hole, and that single black hole decays exponentially. That's what happens here. The black hole neutron star system, the neutron star here gets disrupted, and when the neutron star is disrupted, there is no more clean quadrupole emitting gravitational waves, and the signal rapidly decays to 0. And in the neutron star system, they collide and form a single excited neutron star that brings down at very high frequency for a long time, and that's this mess over here, right? It would be great if we could measure that, because there's a lot more information in that part of the signal than in the early signal. Much cleaner in some ways about what the structure of the neutron star is. It's an excitation mode of the neutron star. It's very dependent on its structure. But
This is much higher frequency.
yes, exactly. It is everything about here is above a kilohertz, and that becomes a lot harder for detectors such as LIGO to actually look at. LIGO is more sensitive in the hundreds of hertz range. So when you get here, even though in the simulations and physically in reality, the differences in the signal is much larger. The sensitivity curve of our detectors mean that it is actually a lot harder to measure it.
And we
Third generation detectors, ground-based detectors such as Cosmic Explorer and Einstein Telescope, right? Those are really aiming. One of their main science case is the high frequency, the kilohertz range, in which you can do very precise nuclear physics with that. Yes. So it will be possible if those detectors be built, and currently the time scale is, maybe I don't know, 20s, 40s, 20, something like that. So it's things that are certainly, currently being designed. There are plans for how to do that, but it's not something that the current LIGO Virgo detectors would see unless you have a very, very close merger. But yeah, it is possible technologically, and there are plans to get there, and there is a lot of information here. And actually, I think my next slide shows this even better. So I'm going to go there. Yeah, so this is a spectrogram of similar systems. And then you have three different neutron star size here for different nuclear physics models. It doesn't really matter which ones. The important thing is you have that late in spiral where the end of the chirp, where the frequency is rising. And then after merger, you have these not quite constant frequency, but pretty well-defined frequencies in the post-merger signal. And the dash curves, by the way, are predictions from a model for where these should be for these specific models, right? So there's a pretty good match between the simulation results here and where we think these frequencies should be. And if you can actually measure these frequencies, you can differentiate stars a few hundreds of meters away in radius pretty cleanly. And if we, by 2040, I expect that the models will be a lot better at this. Unfortunately, this is actually a pretty big neutron star. It's only 2.5 kilohertz. If you go to 12 kilometer, 11 kilometer neutron star that raises to 3-4 kilohertz, this is pretty bad for LIGO or Virgo. Yeah. All right. So this is actually the one thing that has been done so far in terms of measurement of the equation of state with gravitational wave signal is 170817. And you can see that these were, it is the mass for illustration again. You had mass of about 1.3 solar mass, and you were getting from about 10 kilometer or so to about 13.5 kilometer. Fundamentally, the low end here actually comes more from the fact that we know low density nuclear physics and we require causality. But there is no really lower bound on who distorted the neutron star was. This is more like a known physical bound from other physics. The upper bound, on the other hand, is the constraints that come from the gravitational wave signal. And it should not be larger than about 13.5 kilometers or so, according to this image. Right, of course, we need more events to actually reduce these errors. But so far, we haven't had an event as good as 17017 in the 7 years that they followed. But very lucky. This is everything that we have seen so far in gravitational waves, except as of 2 days ago or 3 days ago. I don't remember now when there's a new one, but I'm not in the LIGO collaboration, by the way, so I only know what the public alert tells me about that event. So these are the events that might have had neutron stars that are officially announced by the LIGO collaboration and published with parameter estimation. And you have these two here that are neutron star systems, probably. Definitely 17017 had at least one neutron star because we saw an electromagnetic signal, many electromagnetic signals from it. There's a slightly higher mass systems here, which is also probably two neutron stars, but could also possibly have a black hole. And there are these three here that are most likely black hole neutron star system because the second, no, the lower mass system is most likely below 2 solar mass, and the secondary is most likely above 3 solar mass. So that's very likely a black hole neutron star system. Interestingly, this one is the latest, the one that was announced most recently, just a few weeks ago. It's from last year. And this one lies in a regime in which there could be disruption of the neutron star and there could be electromagnetic signals. This is not the case for the others. The others, the mass of the black hole is too high. The neutron star just falls into the black hole and leaving nothing behind. So you don't get electromagnetic signals or enrichment of the universe in heavy elements for those two. But this one is more interesting in that respect. From the public data release, it seems like the new one is also interesting, but we will have to see. And then this one, well, the lower mass object is 2.6, 2.7 solar mass. So by most existing models, it would be a surprisingly low mass black hole, but yeah, who knows? It could still be a neutron star. So the problem is that to prove, without doubt that there is a neutron star, you need either a strong EM signal that you can associate with a neutron star, or you need to actually measure a non-zero finite size of the neutron star, which is very hard. And so the only system for which we have that is this one here. All the others, the inference we make about whether it's a black hole or neutron star comes strictly from a prior for what the masses should be. And only that. So if there are 1.5 solar mass black hole commonly hanging out in the universe, this could be a black hole. It's just a prior, a reasonable prior from what we have seen so far, but the prior that these are black holes or neutron stars. Yes. No, in fact, physically, you can have even very, very small black holes, like people were talking about for the LHC at CERN, that immediately evaporate from working radiation. You can have black hole from the very, very, very microscopic scale all the way to hundreds of billions of solar mass, and everything is physically allowed. They are completely, they can become rescaled, and mathematically, according to ancient equations, it works. The question is, how do you form them? And if it's like primordial black hole formed during the early universe, then it can be a wide range of masses. If it's black holes formed at the death of massive stars, presumably they are, a few solar mass or more. But, we could be surprised. Now, I don't want to make you believe that one solar mass objects are likely to be black hole. My personal priority is also that they are neutron stars. But I'm just saying we don't know for sure. All right. Anything else? Okay. So I want to switch gear a bit now and go from the gravitational waves to the nuclear synthesis aspect. And in particular, this is a movie that was made by Jonas Lippuner using the Skynet code. This is going to show you how the various elements that are in the matter ejected by a merger, evolve over time. How much of each element we have. On this plot, the vertical axis is the number of protons. The horizontal axis is the number of neutrons. And the squares here in the middle are the stable elements. Right? So here you are very neutron rich, and here you are very proton rich. We are not going to get there. We are going to only get here. And this is an ejected matter, which has initially 95% neutrons, 5% protons. This is pretty typical of what you would get if you disrupt a neutron star and you have cold matter being ejected. That's what you expect. And initially, you have mostly neutrons and then a few low mass nuclei, carbon or oxygen somewhere around there. But as the material expands, it is going to very quickly absorb neutrons on those nuclei. It becomes favorable to absorb neutrons. You absorb more and more neutrons over time, And occasionally you decay back towards more stability with beta decays. And then you run out of neutrons after maybe a second or so, and then all of those elements, which are very unstable, they are extremely neutron rich, extremely unstable, they rapidly decay back towards stable elements. In particular, you get the decay product of elements around here, along those nuclear magic number, and around here, which end up here, which are typical of production in neutron-rich conditions. If you were producing elements by slow capture, which I absorb one neutron, I decay, I absorb one neutron, I decay, I absorb one neutron, I decay, you would produce a very different pattern, which would mostly be due to the properties of elements around the region of stability. Here, what you produce is dependent on which elements are a little bit more stable, very far away from the region of stability. That gives you a different pattern from the S process. In particular, you produce this kind of pattern here. So this is again abundances versus mass number, right? And the red dots are what we infer from solar system observations, what the pattern should be for the R process. And you can see that there's what is called the first peak here, the second peak here, the third peak here, and some elements produced in between. Right? Now, this is the results again from those nuclear reaction network simulations for different electron fractions. It's different number of neutrons and protons effectively, because there are as many electrons as protons. So low electron fraction is low number of protons. So 1% proton, 19% proton, 25% proton here. And you see that if you have a low number of protons, you form these very heavy nuclei, which is what was the second peak and the third peak. And also very importantly, you form the lanthanides here and the actinides here. Those are important because they are elements with a lot of lines, a lot of transition lines, and so very high opacity. That's going to affect the electromagnetic signals. Now you see that if you want to actually match the solar pattern, you also need these elements here. And for that, you need nucleosynthesis in slightly less neutron-rich environment. Electron fraction of maybe 0.25 or so, or higher. And then you see that you don't have enough neutrons to form the heaviest elements, but you are going to instead form something around the first and second peak here. Right? And if you want to reproduce the entire thing, you need a bit of both. In mergers, this comes from the fact that if you rip apart material from the neutron star that is cold, you are going to end up with very neutron-rich ejecta. But if you somehow have hot material being ejected, like from the collision of the neutron stars, or in some case from these winds, that material has a lot of interaction with neutrinos. And weak interactions with neutrinos and neutrons and protons is how you change neutrons into protons and vice versa. Right? And once your material starts expanding, it naturally wants to become less neutron-rich because neutrons become unstable. And so it is naturally going to capture neutrinos or emit neutrinos in a way that transforms neutrons into protons more than it transforms protons into neutrons. Right? So when you have hot material being ejected, it is naturally going to go more toward this kind of nucleosynthesis. When you have cold material being ejected, it naturally goes toward this nucleosynthesis. And we have both ways to do that in nuclear transfer mergers, so we can produce both. The question is whether we do it in the right amounts, of course. And that's not the question we can answer yet. Yes. Okay. Sounds good. So yeah, in terms of electromagnetic counterparts, and that's how we actually can learn about these things, right? How do we know what we produce? How do we know what the merger was doing besides gravitational waves? Well, the important thing is whether we were producing these elements here or these elements here. So if you have a high fraction of these elements, then the opacity of your ejecta is higher. What that means is, as your ejecta is expanding, if the opacity is higher, it will take longer before photons can escape. And so your light curve is going to switch to becoming dimmer and longer lived. Right? So this is if you don't have neutron-rich ejecta. This is if you have neutron-rich ejecta, you switch from a few days for the time scale of the signal to maybe a week. And the color of your signal is also going to change from peaking in the optical to peaking in the infrared. And that again is because of the different opacities of these different elements. This is very important because now if you see a signal like we did for 170817, you see a kilonova and it has some fast evolving blue component and some slower evolving infrared component. You can actually get some information about what was happening during nucleosynthesis and what kind of outflows you were getting, how much hot outflows you were getting, how much cold outflows you were getting. That tells you how much that merger, that gives us some information, at least, that we would like to be able to invert about which elements were being produced, and also what kind of objects were emerging, because different mass of objects, different size of neutron stars are going to give you different types of ejecta. And building that map from the mass and size of neutron stars to the properties of the ejecta to the nucleosynthesis and the kilonova signal is part of what we are still working on right now. It's complicated because there's a lot of physics involved, magnetic fields, neutrinos that are not yet fully captured by simulations. But this is the process that we are currently working on. That at the moment we can actually qualitatively answer. And that's the last thing I'm going to show, I think. I can get there. Yeah. Basically, this is the kind of picture that we have qualitatively at the moment. If you have a black hole neutron star merger, you have a neutron star being disrupted by the black hole companion, maybe, if the black hole is low enough mass. Then it gives you a tidal ejecta that is moving at 20–30% of the speed of light and is very neutron rich. So it's going to give you an infrared emission here, which is very asymmetric, by the way. The geometry also matters. Right? So if you're on this side, you will see it easily. If you're on this side, it will be partially obscured by the intermediate ejecta here. Then you have matter ejected from the winds. And if you have a black hole disk system, the exact properties of that wind are not very well understood right now. That's the most uncertain component, because we don't know whether neutron matter interactions are enough to drive you towards less neutron-rich ejecta or not. This is very uncertain, but it's going to be slower generally, a bit less than 10% of the speed of light, and at least less neutron-rich than this one, because it interacts with the neutrinos. And how much of each component you produce depends on the mass ratio of the system and on the size of neutron stars and on the spin of the black hole. All of these things. So there are the generalities there. But if you use that plus the gravitational wave signal, you can get some information. For neutron star mergers, you still have possibly one neutron star being tidally disrupted by its companion, giving you the same kind of fast, very cold outflows. You have what is called a squeeze dynamic ejecta here, which is the fast ejecta coming from the collision of the two neutron stars and the oscillations of the cores. That one is definitely very hot and less neutron rich. So this is going to give you a blue component. And then you have the winds. And the winds, it's going to depend a lot on whether you have a black hole or a neutron star at the center of your system, which depends on the mass of the neutrons of the emerging neutron stars. If you have a high mass system collapsing to a black hole, it's very similar to the black hole neutron star system. You have a black hole disk system. If you have low mass neutron stars colliding, you have a hot neutron star surrounding by these winds, and the hot neutron star is a very powerful source of neutrinos. That means that you are going to more naturally drive your outflows towards being less neutron rich, because you can absorb a lot of those neutrinos in the matter that is being flung out. And so there again, what we are trying to do is figure out how much of each type of ejecta we have for any given merger, what the geometry is, and then correlate that with the kilonova signals that we are seeing. But that is definitely work in progress right now. I can give you qualitatively, if you give me a parameter of a system, I can give you how these things change, but I can't give you a quantitative answer that I would be confident of at the moment. So that's kind of where we are at the moment in the modeling of these systems. And hopefully, in the future, we'll actually be able to use kilonova to quantitatively give information about the mass and size of neutron stars, like we do for gravitational waves, and also to better understand nuclear synthesis. And I'm going to stop here and take any more questions you might have. Or eat pizza, I don't know.
Any more questions?
So thank you very much. I have a question, actually, a question and actually a news for you that you might be interested.
Okay.
So the black hole neutron star that has been discovered 2 days ago.
Yes.
Actually, we have an X-ray counterpart.
That's great.
Yeah, there will be GCN in a few minutes. So which is, we know the flux, we don't know the distance exactly, but let's say
From 3 days later?
luminous, just 22, now it's 26, 4 days after the merger.
Okay.
So in your modeling, where is this coming from exactly? This
4 days.
X-rays. It's the accretion on the black hole leftover, it's the jet, it's what it is.
I would have to look at models for afterglow of GRBs to know exactly what the time scale is for the jet. This is not really my, but I can look at it.
This was not the GRB.
There was not, yeah, but could it be the afterglow of an off-axis GRB? Or is it too short? It might be too long, like 4 days might be too long already.
4 days.
It seems very long, right?
Yeah.
So, I mean,
And we know
Yep.
it's a black hole neutron star
Yeah,
matter because
and-
from
yeah, right. I mean,
But the
then it,
was not
I mean,
existing.
accretion is possible, but it's because we were hot, but it's yeah, it's a little strange.
Sorry?
How do you know it's the same event?
Because it's in the circle. It's the only X-ray transient event in the error circle.
Yeah. I mean,
For
yeah,
this, it's
Now
not
we have
too-
Lil
for this, it's not too much.
it's not too much for the GRB after all.
Or- No.
But then,
because
I mean, if it can be a GRB after all, that would be natural gas.
And
The
also
GRB
in the,
itself
also
was
in the.
not-
Yeah, if you're off axis, off axis from the jet.
Also in
GRB axis from the jet.
1708,
Yeah.
there was no GRB, that means that GRB that we observed was not.
Well, it's a low luminosity.
I think it's by gamma ray. I think it's by gamma rays.
Yeah, yeah,
But yes, no, it was off axis, yes, and if it is even slightly more off axis, we could. So I don't know off the top of my head the time scale for afterglows of GRBs, but if it can be that, that would definitely be my first guess. If not, yeah, we would have to look at accretion. That's more complicated, but.
How much energy? How much energy? is it? What's the luminosity?
Oh, we have the flux for the moment because the distance is not really well constrained. But now that there is the extraposition, there is a galaxy close by, so probably the redshift of the galaxy will be
And,
released.
We get a lot of
Give
suppose
that few
optical
hours.
infrared,
Yes.
a lot of optical infrared observations coming up with the galaxy. I'm assuming.
And so in this case, do you expect then the kilonova to switch on in a week or so?
In a black hole neutron star merger, there is a possibility of a bluer component, but we would generally expect that the core of the kilonova is colder material. Yes, on average, it should be longer duration, more red than for an NSNS system. Yes, there can be some blue component from the disk ejections that would come on time scales of a few days, but it will depend on the exact parameters of the system. But I would expect that you would get more naturally the infrared slow evolving component. Now, when we still can't explain 170817 properly, right? So between my expectations and the physical reality, I mean, we'll see. That would be my guess.
And from the LIGO point of view, so the fact that there is this high probability of black hole neutron star in the system, can that actually be a neutron star that was?
Well, I do not know the chirp mass of the system, which LIGO might have an idea of. So from what they tell us in the circular, right, is that it has 100% chance of having an EM counterpart according to the formula that I wrote, which means that it's either a neutron star system or a low mass black hole neutron star system or a high spin black hole neutron star system. And there's a 50% chance of a mass gap object, which would make it definitely a black hole neutron star system. But I don't know where the other 50% is. Is it lower mass or higher mass? And it could be both.
In principle, we cannot be for sure.
Anyone involved in LIGO who knows the chirp mass would probably know the answer to that. Well, it's an idea of what the chirp mass is, would probably have an answer to the questions. I don't have that information. But anyone in LIGO who has the chirp mass would be able to tell you that. And that's why I wish they would actually release the chirp mass, because it would inform the observations. Even if they have only an approximate value of it.
More? Do you have any online? Thank you very much. It was really wonderful.
Thanks.
And no, my question is that there are there are some problem for the enrichment of process element from
Yes.
compound binary
They
narrative.
definitely are.
Yes, that require maybe some younger population. of
Yeah,
that compound
yeah, so
binary
that's one issue. So we can pretty easily produce the range of elements that we need. Within the large uncertainties on the event rate, we can produce the amount we need, but we will have to reduce that uncertainty with more LIGO observations, various observations, maybe even search engine detection in the future, and hopefully check actually whether it matches or not. Also, we need both the event rate and know how much matter is ejected on average by a system. So what type of event are actually merging is important. Like those high mass black hole neutron stars great for LIGO sources, but they're not going to produce any elements. So it doesn't matter.
Can they
Uh,
for
but-
example, in,
yeah.
the enrichment of I don't know low mass galaxies?
Yeah, so that's the problem. Is how do you? So there is some component of enrichment which which seems to happen on the time scale more consistent with star formation than the delayed merger, and that is a potential problem. I mean, there are channels that give you faster merger in more dynamic environments, but it's very uncertain whether they can get there. So yeah, having some other way of forming elements on a time scale that is more consistent with star formation, like supernovae, helps with that. And so that's one of the main drawback of the merger scenario for enrichment of the universe in heavy elements. The kind of strength of the merger scenario that we have actually seen are processed in mergers, while we have not seen it in supernovae, and the simulations are very uncertain of whether you can even do it in supernovae at the moment, right? But yeah, we have to take into account those observations of low mass stars, which do show our process enrichment, and it's harder to do with mergers than with some faster scenario. Yeah, so that's certainly one argument for potentially two components in the R process, and then you would have to figure out which one is the most important in practice. But yeah, that's a very important point. Yeah.
Anyone quick question? Good? Yeah.
Not on this topic at all, but it's over the innermost core of
Sure.
what happened? Just to go.
Well, the core itself generally is not disrupted. The really core, the part that forms the disk and the ejecta, it's a few percent, 10% of a solar mass or so. The cores themselves collide and merge and form a more massive neutron star or collapse to a black hole. And so, what might a more likely scenario than the core being disrupted and becoming something else is two low mass neutron stars that don't have that phase transition, forming a more massive neutron star, which then transition to a higher density core that has that weird matter. And that is a more likely scenario in my view than one neutron star being disrupted enough to actually change that weird core into a normal neutron, proton, electron gas. That being said, I mean, yeah, if you are very close to that transition, as neutrons are distort, it lowers its density. So you could have phase transitions during the inspire. It's possible. You would have to be pretty close to that limit. But if there are neutron stars pre-merger that have high enough density to see that phase transition and are very close to that boundary, there could be some weird effects during the late inspire. Yes, I think it's less likely than a phase transition during merger, but it can happen.
Okay. Last chance, very last chance. If not, we should probably.
All right. Well, thank you all.
Yeah, I didn't realize.
I love your